I hope everyone had a chance with the extra time that you had to at least watch the 3 videos that I pointed out, especially if you had not seen them before, either this weekend or in the past. If not, I highly encourage you to watch them after the GP. You should all be aware that this week, we've already talked about it, but this week's going to be a little bit different in terms of the length of the independent project and the length of the sprint this week. So you will have until, there will be a GP every day, Monday through Thursday, at 11 o'clock Lambda time on Thursday. You will be given the link to the sprint, and you will have until 11 o'clock on Friday to complete that. And of course, until 5 p.m. to get the MVP completed. Then after that, we will be changing over to the format that they discussed in Assembly today. So if you weren't caught up in Assembly, get caught up with one of the postings that they made, and you'll get more information on that. But that's kind of how things look. So it's a difficult week. It's a dense week with a lot of material. If you've never seen it before, it's definitely not the easiest week here, but we're going to all get through it. I'm going to go ahead and get started.
By the way, can I ask, what's GP stand for?
Guided practice. Guided practice, lecture, the demo, all one and the same. It's simply talking about the topics that are on deck and doing live coding and kind of, I don't know what the word for it would be, group coding, where I kind of lead the code itself, but I get a lot of input from the group. We got quite a few people in here, so a lot of times I let people during the live coding unmute their mics. We can continue to do that as long as people aren't talking over each other. If that starts to happen, we'll just go back to typing in the channel, and still feel free to type anything in the channel, especially short things. But during the GP, I'll let people know, like when we're doing the coding, you can open your mic if you wanted to make a comment. I'm going to go ahead and get started after I... I'm going to go ahead and share my screen. So this week we are going to be talking about graphs. Anybody in the channel want to type out and tell me what a graph is? A simple definition of a graph. What is a definition of a graph? I see several people typing. A system of connected nodes, collection of data that is interconnected, a collection of data represented by nodes and connections between nodes. Yeah, excellent answers, and more or less that is a simplistic way of defining a graph. They're an extremely powerful and diverse data structure that represent relations between data. They can represent anything from a social network, web page site maps, flight patterns, user behavior, and much more. If you have relationships, you can build a graph from them and utilize operations like breadth and depth first searches that hopefully you saw in the videos this morning that you had extra time to watch, to gain powerful insight into those graphs. They're interesting, they're diverse. You'll learn to recognize and solve almost any graph problem you come across through this unit. There's a lot of takeaways from this. I'm not really going to walk through them all. I can pull them up and talk through them, but the big takeaway is that we're going to learn how to represent data as a graph and learn how to implement a lot of these graphs in several different ways, and ways of traversing these graphs and ways of working with these graphs to achieve our desired results. So you had your pre-course material that covered the graph basics, the breadth first search, the depth first search, and there was also some reading. We've talked about kind of what is a graph. Somebody give me a real world example of a graph, and some type of an example of a graph. Facebook is a graph, but what else? There's plenty of different examples we can come up with, and then we'll talk about some basic terminology of those graphs. Somebody give me an example of a graph. Yeah, navigation on GPS, because it's doing a lot of different things. It's looking for the shortest route. So there are components and uses of a graph definitely to find shortest route. In fact, it's one of the most classic uses of a graph to find shortest route. Subway stations map, yeah, exactly. Kind of the same as a map, where you're looking at interconnected points on a map and how you can traverse those points given the directions that they go. We'll talk about things like that. Another thing about navigation on GPS, it can also find not only the shortest route in terms of length, it can approximate the time, and we'll see what can be utilized with a graph to help be able to do those different things. There's two types of graph. There's our directed versus undirected graphs. A directed graph is the same as pointing in one direction. So don't be confused by calling it undirected versus directed. There's always going to be directions that there can be a traversal, but with a directed graph, you can simply traverse from 1 to 2. You cannot go back from 2.1, 1 to 2, 2 to 5, or 2 to 3, 3 to 4. Here we see the arrow pointing backwards, or you could have it right here as well. But a bidirectional or undirected graph goes both ways, as we see here. 3 can traverse to 4. 4 can also go to 3. So a real life example of this and how it may work would be Twitter. You can follow somebody on Twitter, but they don't have to follow you. So say you're person 1, you're following person 2, but there's not a connection back to you. Whereas on Facebook, you're friends or you're not. And if you're friends, there's a connection going both ways, and we will dive very much into that later in the week with some of the code that we work on together when we actually simulate a very basic social network and perform some actions on that social network. So a directed graph simply points in one direction, is able to traverse in one direction. A bidirectional graph can traverse in either direction, from one node to the other and that node back. There is cyclic versus acyclic. Cyclic means you can start at one point and traverse the whole graph and come back to that point. Acyclic simply represents otherwise. You're not able to do that. So you can have a graph that had, if the graph had all undirected components, bidirectional, where everything connected to everything both ways, obviously that graph is going to be cyclic. If you have, I'm trying to think if there's any examples where that's not the case, because there's always the edge cases. You can have a graph that has some unidirectional points, where it is undirected and both nodes can traverse to each other. And it not be cyclic. So cyclic simply means you can traverse the whole graph. Think of it like a cycle and keep going in a loop. Acyclic means that is not possible. And we'll go on into all of this, and we'll be using this terminology a lot, but I'm just trying to go over the basics of it right now before we really get started with the code. There's also dense versus sparse, and this refers directly to the amount of relationships in that graph. So say a way to think of it is if you have a social network that has 100 people in that network and everybody has 10 friends, that will be a pretty sparse graph because each person is only connected to 10 other people. There is no numerical cutoff, no set definition of when you go from sparse to dense. But think of dense as, the epitome of a dense graph would be where, like I was talking about, everything was connected to everything. Everything had undirected connections, bidirectional, where the arrows are pointing both way and you can traverse in either directions, like a Facebook relationship. It would be like Facebook and everyone being friends with everyone. A sparse graph, you have few connections. There's also weighted versus unweighted, and that's our final thing. And this really isn't represented here. One way you can think of it, though, easy, is that basically the connection, each node may hold a value in itself, whether that value just be the name of the person, or it really depends. It can hold anything you want. But the connection itself can be weighted or unweighted. A lot of times you simply see these as unweighted, but many other times you see them as weighted. Weighted simply means there's some sort of a value associated with them, usually an integer, maybe a float. What makes sense here with a weighted graph? What use could we make of a weighted graph? What use could we make of a weighted graph where the connections actually held a value? And let's say the length of, not here necessarily, but the length of the arrow connecting them also was represented by that value, let's say in some sort of a scale for the length. What would be a use of that? We talked about it earlier. There were some real world examples people gave. Yeah, comparing routes on a map, that weight could be time. That weight could be distance in kilometers or feet or meters or miles. You could have many different examples of that, but that is a perfect example and very classic example of comparing routes on a map. Thing I wanted to grab real quick. We can kind of move on. I'm going to put up a survey real quick and just ask if anyone has any questions over these basic definitions. If you have anything, just post it. I'm going to make it anonymous and add the choices, simply yes or no. Just vote no if you don't have anything. If you have anything, you can speak up in the channel by voice, or you can type it right here where it allows you to add things. Give just a second for that. I'm going to pull something else up. Six no's. We've got, including 13 people on the channel, so 7 people, 6 more people haven't voted. Everybody vote. If you got a question, giving you a chance to ask. Directed versus undirected, it means the connections between the nodes, whether it's a one direction or whether there is 2 directions, like Twitter versus Facebook. Cyclic versus acyclic. Think of it if you can make a cycle, if you can go all the way around the graph and keep moving around or not. Dense versus sparse. How many connections each node has relative to how many total nodes, how many total users, however you want to think of that. Weighted versus unweighted, putting values on the connections. Got 11 votes. I have a problem implementing BFS in last sprint. Would be great to go over it sometime. Yeah, we will be going over part of that today and part of that tomorrow. And if you need more help, especially since you struggled last time, we can meet about that one-on-one. We definitely will be addressing that here today. We've got about 45 minutes left today, and what we don't cover today, there is more material tomorrow, and we will make up for anything we don't cover tomorrow. Plus, during the independent projects, your repo, you'll be working on that as well. All right, looks like everybody pretty much has voted, so I will keep going. There's basically 2 different ways to represent a graph, an adjacency matrix and an adjacency list. The simplest way to think of these is an adjacency matrix. Excuse me, quick drink of water. Sorry about that. Maybe my tongue won't get tied up. An adjacency matrix, think of an adjacency matrix like a 2D array. So with an adjacency matrix, you're representing every possible representation being an index. Remember, a 2-dimensional array will have 2 different index points. And you're representing A to A to B, A to X, B to A, B to B, B to X. You're representing every possible relationship. And classically, a 0 represents no relationship. A 1 represents a relationship. So A is connected to B in this case. So that's A is connected to B, like we see here. though B has no relation with A because it's not bidirectional, it's only unidirectional. Directed here, one direction. These are actually pretty rare. We're not going to cover a lot of this. There is one special case with space complexity. Remember, we talked about not only do we have to think about the number of operations that we're doing, not only do we have to think about, we call it time complexity, even though it doesn't involve time, but a lot of times the number of operations we perform directly relates to time. But there's also space complexity, how much memory we're using. And when we get into very complex operations that can use a lot of memory, you start chewing up RAM, you have to start going into the hard drive itself, you start slowing things down. And remember, a lot of times, especially as developers, our end goal is very expedient, efficient operations because users want that. Users don't want to wait 10 seconds to log in. Users don't want to wait 15 seconds to get an answer back from their query. They want to hit enter and boom, have answers right there. So we will talk about one case with a dense graph, why an adjacency matrix has better space complexity. We will be representing everything in an adjacency list. I have never seen anything outside of an adjacency list in the real world or in academia other than the kind of 101 coverage of an adjacency matrix. I remember Brady also commented he had never seen a real world application of an adjacency matrix. So with an adjacency list, what you see here is like a dictionary, an object, and the key is simply each node, and then the value is each of that node's connection. So we see A has a connection to B. B, we see, has a connection. Well, in this case, I'm pointing down at here. I was looking at the wrong one. A connects to B. B also connects to X and P. B also connects to T. So B connects to 4 different points. So we see that A, X, P, T. I'm sorry I was pointing down here. It was relative until I realized we were talking about this graph. Then X only connects to B and P. So you see how we do this. Each node is a key, and then the value will be all the connections that node has. So in terms of space and in terms of time, can anybody think of some advantages or disadvantages of accessing these and the space required for these? Accessing these and the space required for these. Give a few minutes for people to type. Seems like with an adjacency list, you repeat connections, example A to B, B to A. But remember, look here, yes, you do repeat connections here with an adjacency list, A to B and then B to A. But remember, this is representing that A has a relation with B and B has a relation with A. You also do that here. A does have a relation with B. B does have a relation with A. So the problem with the adjacency matrix in terms of space is that you have to have a data point for each possible relationship. Each possible relationship, you have to have a data point. With an adjacency list, we're simply using sets, which I'm not going to get into too much. A set, think of it as an unordered list. There are not indexes. These could be in any order, and a set does not have repeats. In other words, you cannot have 2 A's here. B can't have 2 relations with A. So a set is a mathematical thing. If you want to know more about it, Google on it, find a good resource and read about it. But just know for now that a set that we'll be dealing with, and we'll talk about more in Python, is unordered. These can be in any order. It's not like a list in the terms there's the 0 and the 1 and the 2 and the 3 index, and there's no repeats. So an adjacency list is a dictionary with keys for the node, and the value is a set that contains all of its relations. Whereas a matrix has to represent every possible relation. So the matrix is less efficient with space. The one case where that's not the case is if you have a very dense graph, like we were talking about, a social network where everyone is friends with everyone, and so all of these relations are ones. All these relations are ones. And in this case, A would have a relationship with everything, B with everything, X with everything, and so forth. In other words, you're having to represent each of these points in both graphs like you're talking about, Brian, when you said an adjacency list, you're repeating. Well, in this case, you're having to represent them all because there's a relationship between them all. And in this case, because of the way that things are stored in a dictionary versus the way that things are stored in this two-dimensional list, this two-dimensional array, you actually have a better space complexity with an adjacency matrix. That's all we're going to talk about with that, but with an adjacency list is what we use. It is what you generally will see. It's what almost always comes up. Just wanted to make you aware of these different options. So right here, and I can drop this link. It should be, but if anyone wants to navigate right to this link, you should be able to get to it right here. And I just have the example with the dictionary of the adjacency list and the two-dimensional array, the adjacency matrix that we have. And the trade-offs like they discuss here, they have their strengths and weaknesses, and the space complexity is what we talked about. An adjacency matrix has a space complexity of v to the second power, v squared, the number of vertexes, the nodes, also called vertexes. I forgot to mention that earlier. E, the edges, that is the official name. I was referring to them as connections. And then the little e, average number of edges per vertex. Remember, that's the density. So for an adjacency matrix, we have v squared, whereas for an adjacency list, we have v plus e. Remember, those are going to be, that's basically the same as what time? O to the n or O to the 1. And I think Tony said it above O to the n for an adjacency list because we know when we evaluate time and space complexity, you can say v plus e, but we would call this O to the n in the notation because that would be the same as saying n plus n, which is 2n. And that's simply n. So O to the n for the adjacency list, Tony. We talked about what they're talking of here, the sparse graph versus the dense graph, though this adjacency list, worst case, would be v squared if we approached a completely saturated, a completely dense graph where everyone was friends with everyone on that social network. And in that case, based on how they are stored, the adjacency matrix is your best choice. We'll go real quick. You can read more on these later through some of the time complexities. For adding a vertex for an adjacency matrix, it's O to the v, the number of vertexes, because think you will actually have to iterate through those, and you'll be adding the point at both. With an adjacency list, remember, we're just simply adding a relationship here. With an adjacency matrix, we've got to deal with the complexity of the matrix. So they kind of explain here, you just simply add to the set or create a set with that edge being the first member of that set. If that set is empty, if there's no connections until you create one. With an adjacency list or an adjacency matrix, they show here you have to add a new value to the end of each existing row, then add a new row at the end, a new row, because you have a new set of possibilities. Even though you've only added one connection, now you have a whole new set of a new vertex, excuse me. Now you have a whole new set of possibilities of relationships with the other vertexes. So therefore, it is O to the n time. Removing a vertex, once again, on a matrix, because of the problem that you have, it's going to be v squared because you have to deal with that entire matrix. With an adjacency list, it's O to the v. Adding an edge for both a matrix and a list is one time, because when you add an edge, remember, a connection, all you've got to do is change one of these from a 0 to a 1, whatever point. All you've got to do is add, say you added a connection to D here, you just add D. That's one time, it's a single operation. We're not having to iterate through, we're not having to add anything, add any more possible connections. Removing an edge is also the same, O to the 1 time. Finding an edge is also O to the 1 time with both of them, because we can look up the particular indexes for a matrix, or we can simply look for that in the dictionary. Remember, dictionaries are very efficient in terms of lookup, but in terms of the matrix, we know both of the points. Does A have a relationship with B? So those are both O to the 1. If you want to get all edges from a vertex, in other words, all the relations that that node has with other node, an adjacency list, you just ask to return the set. For an adjacency matrix, however, it's more complicated. You've got to iterate through the entire row that is represented by that node and return the ones that actually are, in this case, the ones. So I'll ask again real quick. I went over those fast, and I don't want to spend a lot of time on those. You can read more on those later. But I just want to ask, are there any questions right now? But this is something you can refer back to with the link. You can go over these in detail, but just know in general, like I said, we're going to be using an adjacency list. The lists in general perform better than the matrices, the same or better in terms of time complexity, and they perform almost always better in terms of space complexity, unless you have a very dense graph, which in the real world is not normally the case. So I'm going to post this, and then we will move along with some code. Give about 2 minutes, a minute for people to answer that, and we will move along. But you've got this list. You can go back over this on your own. It's not something I need to sit and talk about. These all should be pretty self-explanatory. If you have a question regarding some of these time complexities or the space complexity that we covered that relates to these, get with your PM, get with me, post in the help channel, and we'll get you helped out. But these all hopefully are pretty self-explanatory after the videos and after this. And just one more thing I wanted to go over, and I kind of touched on it, but why do we use a set? It's because edges in a graph are unordered. They don't go in a 0, 1, 2, 3 index type order. So a set, like I said, is a mathematical definition that's represented computationally in many different languages. Python gives us these sets. Think of it, like I said, as an unordered list. The edges are unordered, and the set allows you to check if two vertices are connected in O to the 1 time. You'll learn why this is the case. It's O to the 1 time in a few weeks when we cover hash tables. But for right now, just know that a set is unordered, so it's conceptually similar, exactly alike to a graph, because edges are unordered. It allows you through hash tables to check if two vertices are connected in 1 time. Anybody else want to vote? Looks like about 4 people haven't voted. I'm going to keep moving. If nobody, we were going to implement an adjacency list. Give me a second here, and I will get this set up. So as we've been discussing before, all of these data structures that we have been implementing, we have been using classes. Classes are, why are classes good for these data structures? We've talked about this in the past. What makes a class, it's one word I'm looking for. It could start with an R. I guess you could use a few words, but what is one big reason, but list any reasons you can think of, why classes are good to use for data structures? Other than the fact we're going through OOP at the same time and touching on that, why are classes suited well for data structures? And I'm going to type while you are typing as well. Thank you to the people that are answering. And so let's see what we got here. Class instance remembers its states, inheritance. Brian, you were getting at the main thing. Yeah, you could, you definitely can use inheritance, especially in the more complex data structures. Class instance remembers its states. The big thing, the simple thing I was using for these are all good thoughts is the reuse. You can simply instantiate another instance of that class when you need a new, in this case, you're about to see a new node for the graph, or you need another instance of the entire data structure or whatever it may be. It lends itself to readability and being dry and being able to reuse itself. So for the class, we have the init statement that we have evolved with, have self.vertices, and we will store that. Remember, we're using an adjacency list. So we will set up our vertices, and that will be empty. And then we will have a method add vertex. We'll say self, and we'll have a vertex ID. That will simply be the value of the vertex. That could be the name of someone on a social graph. That could be a simple number assigned to a user. And we'll say self.vertices with the vertex ID equals set. So if we want to add a vertex, a new data point, we have to make a new set, because remember, we were looking at earlier, each time we add a point, we add that point, that's our key, and our value will be that empty set. And then we will also have add edge. Remember, these are the connections. And for this, we'll have vertex 1 and vertex 2. If we need to add an edge, remember, so if it's bidirectional, we only need to add an edge between A and B. If we also needed to do or excuse me, if there's only a one-way relationship, you only have to add between vertex 1 and vertex 2. If there is a relationship in both ways, you would also have to add vertex 2 to vertex 1. And we'll see a real-life instance of that in a day or two with our social graph. So we're adding an edge, so we need to know which vertexes we are adding. And we will simply say if v1 in self.vertices and v2 in self.vertices. Someone tell me what we're doing here. Why do we have this conditional? Why do we say if v1 in self.vertices and v2 in self.vertices when we have a method for adding an edge to this graph? Why do we need to say if v1 in self.vertices and v2 in self.vertices? For any of you guys that are new, I appreciate all the participation that's going on. Something I always just kind of tell about myself. To prevent an error where nodes do not exist. So this is simply checking to see, is there, if it's say add edge between A and B, do A and B exist? If they don't exist, we're going to have to go back and add it, or we're not going to be able, you can't be friends with someone that doesn't exist in the social network that I keep using it as an example. So we can say self.vertices v1 add v2. And know that that add, this right here is Python specific syntax. This has nothing to do with up here and these methods that we've defined on our own. We're simply adding a vertex or adding an edge to that vertex by accessing that vertex and then adding to the set. Adding v2 to the set. And then we'll just have a little else here for housekeeping, and we will raise an index error. We'll just say that vertex does not exist. Anybody have any questions? If you have any questions over this, you can speak up in the channel on your mic or type. I don't want to take the time to make another one. We're simply initiating this graph. We start out with no vertices. If you want to add a vertex to this dictionary, we are simply adding the vertex ID that we supply. That could be a username, it could be a string, it could be a number. We're creating a new set for that vertex, because when we add one, it doesn't have any relations. And we're adding an edge. We're just checking if both of those vertexes exist. And then for V1, where we're adding the relationship, say it's A, we're adding V to the set. Yes, and if it was if this would be a directed graph, V1 to V2, A is only pointing to B. If you were needing to, you would simply have to add an edge both times or have some customized code. If every time that you established a relationship, every time someone accepted a friend request in Facebook, it automatically makes it to be undirected because A is related to B, B is pointing at A as well. Does that answer your question? So you'd have to write some different code, or you'd have to do it twice. And it's something in a social network that matters, and we'll see the math behind that in a few days. But yeah, it sounds like everybody's got the idea here. Remember, this would simply be for a directed graph. I'm going to talk about starting today, and like I said, you've had the videos, and we will continue to cover on this tomorrow as well as with tomorrow's material. But between what I go over and between the videos that you have and then your PMs and the help channel, you should definitely be fine for today, for what you're working on today. Does everybody have the link to your repo? So your repo for this week, if you don't have it for some reason, it's here. This repo will last through the entire week. Remember to follow the workflow, fork it, clone it down locally, branch it, make a change, push up, add that branch to the GitHub, make a pull request, add your PM as a collaborator immediately. This repo will include the entire week. And actually this repo, unless it's changed, will also include the sprint challenge. As you see for today, you'll be going over graph traversal and search for your independent projects. And you'll be implementing a graph class, which we're already working on. Then you'll be working on a breadth first traversal, and you'll be working on a depth first traversal with a stack, then a depth first traversal using recursion, breadth first search, depth first search. Let me be clear right now the difference between a traversal and a search. A traversal is designed to touch every node in the graph once. You'll see that much more clear when we go over some of the code. when you traverse, you never touch the same point twice. You never perform whatever operations you're currently performing on those nodes, whether it's simply seeing if they match a value, if you're manipulating the value. You might have to say, have I already visited here? Yes, and then continue on, but you never will perform is anything other than just saying, has this been visited or not? A Boolean answer. On a search, and a traversal will traverse through every node of the graph. A search is the same as a traversal, but it's looking for a particular value. So we're saying, is Steve in these 10,000 users, these 10,000 nodes, these members of this social network? And once a search, if it's not there, a search will be the same as a traversal. It will traverse the entire graph. It will terminate because it didn't find anything, and then it'll do whatever you tell it to do from there. A search will terminate if it finds what it's looking for. It's, by logically and by nature and kind of by definition, it will terminate once that search is finished. That's what you'll be working on today. Going back to the code here. So think about, somebody tell me what breadth first traversal, in their own words, how it works. Yeah, Jawad, you say it traverses across before going down, and that's why I kind of pulled this up, because I wanted to, even though it doesn't always pan out like this, it's the simple way of thinking of it. So we think of this node, and then this node is connected to nodes, and this node is connected to other nodes. And remember, this can get much more complex, but a breadth first simply starts here, and then it looks at the neighbors, okay, and it's going to look at all of the neighbors. Then it's going to look at all these neighbors. So as you're saying, it traverses across before going down. Yes, in the classic representation that we use often, it does traverse across. So it checks each level. This is the neighbors. This is the neighbors of the neighbors. This is the neighbors of the neighbors of the neighbors. A depth first search, anyone want, or traversal, how does that work? How does a depth first goes down each node? Yeah, that's pretty much what I was looking for. A depth first goes all the way down the depth, and of course you'll have to figure out the logistics of doing this and not touching the same point twice. But we'll talk about that more in a bit. The depth first goes all the way down. It's not concerned about going level by level, and we'll see the difference between using a queue and using a stack for each of these. So the breadth first traversal looks at the nodes one node away, then all the nodes two nodes away, then all the nodes three nodes away. Note on a graph, this could start at any point as well, so that adds some complexity to it. But think of it, it looks at all the nodes, one node, two nodes away, three nodes away. It looks at each level. It goes across before it goes down. Depth first goes down first. It looks at all the levels, the neighbor, then the neighbor, the neighbor, then the neighbor's neighbor's neighbor, etc. And remember the difference between a traversal and a search. The traversal walks through an entire graph in a depth first search or a breadth first search order. A search will look for a node and usually will return a path. So once it finds that node, it will say the way that it got to that node. And there are differences in whether we use breadth first or depth first to find that node and the implications of whether that's the shortest path or not. But more of that to come. So if we were going to code breadth first traversal, So say we wanted to say depth, and we will say BFT for breadth first traversal, and we will say self starting. Remember, we can start anywhere. Starting vertex ID. Then kind of pseudo-coding this, we will say empty queue. Is everybody okay with the size, or do you want me to, is this better at this size? Realized it's a little bit small. Good. So we're going to create an empty queue and on queue the starting vertex ID for a breadth first traversal. Then we will create a set to store the visited vertices, excuse me, get that correct. And then we can say while the queue is not empty, and we can say DQ the first vertex. And this is what we're talking about. And when it said, okay, has it been visited? If that vertex has not been visited, we will mark it as visited. And then we will add all of its neighbors to the back of the queue. So for breadth first, we'll be using a queue, and you'll see for depth first that we use a stack. And a depth first is almost the exact same as a breadth first, besides we are using that stack. So if we actually were going to code this out, I'm going to walk through this kind of quick, but I would say that queue, and we'll simply make a queue. Remember, this is assuming that we have a queue backing this, a queue data structure backing this. So it's going to throw an error here, but we would say queue, and then actually, excuse me, on queue the starting vertex ID. So we have the starting vertex ID. So we've implemented a queue data structure. Somebody tell me, in terms of in and out, what does a queue do? Last in, first out, last out. What does a queue do? Queue is first in, first out. Stack equals last in, first out. Exactly. So we create this queue. We on queue the starting vertex ID. We create a set to store the visited vertices. So we will just say visited equals a set using the Python syntax while the queue is not empty. So we can say while queue.size is greater than 0. We got to have something in the queue if we're going to be checking the queue. DQ the first vertex, so we will say v equals q.dq. If that vertex has not been visited, so we can say visited.add v. if it has not been visited. So after we DQ, before we add it, what we will have to do, we can say if the not in visited. This is simply saying we got our view, that's what we've DQ'd. We're checking if it's been visited. We're using Python syntax to check, has it been visited? And if it's not in visited, we simply add it to visited. I was wondering why that was throwing an error, but if anybody sees me leaving out a colon, sees me my spacing messed up or it's throwing errors, feel free to jump in and point that out. It is something that I do occasionally. And we can just kind of, for housekeeping, we can say print D here. And then I'll actually move that to here up under market as visited. And then for all of its neighbors, add all of them to the back of the queue. So we can say for, yes, you do need to import the queue, and I don't have that here because, but yeah, you would need a queue. And you'll see in here, for your work, you'll have the from util import stack and queue. So already in this utility file, you've got your queue and your stack, but you should be very familiar with those from covering those in the past, but these will be available. So if we just took this, we copied it, let's just say up above all of this, we implemented it. And then you now wouldn't even have to do an import because you have got it up here. Same difference. That answer your question, Yanrong? It will be available to you, and I should have had it sitting in there, but with everything going on with the assembly and the time this morning, I didn't get set up quite perfectly like I would usually like to do. So then we're saying for next vert in self.vertices, still going through the vertices, for the next vert, we're simply going to on-queue it. So in short, if we've got a graph and we want to do a breadth first traversal, remember the way we talked about traveling across in the classical, going level by level in the classical definition, or the classical representation of the graph like we showed. We simply create a queue with what we had up here that we've gone over in previous weeks. We on-queue the starting vertex ID, the starting point that we want to do this traversal from. Remember, we can start anywhere. Then we simply make a set. Remember, a set works well because you can't use repeats and it's unordered. And we will see why accessing things in a set is like using a hash table. It's using a hash table, and it can be done in almost one time. You will see that here in the coming days. Just think of it now. You're able to access in one time. That makes it time efficient. Therefore, we're using the sets that Python allows us. Feel free to do more reading on those in the documentation online if you want. While the queue has something in, while the queue size is greater than 0, remember, we're going to have to go through the entire graph until the queue has nothing in it. You simply dequeue the first item, and then you're going to say, if V not visited, we're going to check to see if it's been visited before. We'll print it. We'll add that to visited. And then if it's not been visited, we will also add all of its neighbors to the back of the queue. And you can see in this manner, you go back and think about it in this way, everything in the queue is first in, first out. So everything in the queue will allow us to traverse in that left to right, that across that depth level first, because I think I already took it off, but if I were to go back to we went back to something like this, like we were talking about. So say the starting point was 1. So what would we do? If we would on queue the 1 and we would add it to the visited. And we would dequeue the 1 because the queue dot size is simply 1 at this time. It's got 1 node in it. And it's not in the visited, so we will add it to the visited as we discussed. Then we'll add all of its neighbors. So we're going to add 2 and we're going to add 3 to the queue. So you continue to add the neighbors, and you can see in that using the queue allows us to traverse in that breadth first manner. And I'll go over this real quick. We're right at the hour right now. If anybody's got to jump out, go ahead and jump out. But I'm going to go over depth first traversal as well. I'm just going to make some changes. This pretty much covers what we were supposed to cover today, other than going over some theory at the very end. But for the depth first traversal, and if we wanted to call, I'm going to make some changes in here. Yeah, go ahead and run if you need to. The video will be posted later, and you can, this is all in your material that you have, and I will post all of this code when we're done as well. So we're going to make a stack instead. We'll just say create an empty stack and push the starting vertex ID. Remember, we push onto a stack. What's a stack in terms of, we already talked about it, somebody's stack last in, first out. And then for here, we will simply say stack.push. Starting vertex ID. We will create a set the same way to store the visited vertices. We will then say while stack s.size is greater than 0, while the stack is not empty, we're going to pop the first vertex. So v equals s.pop. Remember, this is going to be the last in, will be the first out. This will allow us to keep checking the neighbor, the neighbor of the neighbor, the neighbor of the neighbor of the neighbor. And then we'll say if v is not visited the same, print v, mark it as visited. I guess actually mark it as visited would be best if we moved this. The print and the visited.add makes more sense. We'll print it, we'll add it. Well, for the say for the next vert in self.vertices, the same way we're doing, and we will simply say stack.push as we're doing, adding to the end the same push pop terminology that we used in JavaScript. the fact that I didn't indent there. So we're doing the exact same thing here. We're going to the top of the stack. And we will call this pop, the first vertex. Same thing here. I'm going to go ahead and just take any questions and let everybody go on. So I will say poly. This is covered. Again, if you need to go, feel free to go. This video will be posted when it is done later. Processing. And part of what you'll be able to see today is that you will be able to see, as you're working on these, maybe if it's not clear right now, and if it's fine if it isn't, why does a queue work for the breadth first while the depth first we want to use a stack? And it's simply the order that we're adding them versus the order that they're removed, the first in, first out, last in, first out on the stack. And it probably will make a lot more sense as you are working on them. But if you have any questions, please post them in the channel. Please reach out to your PM, reach out to me. Let me go back and see. Anybody have any questions? Post them now. I will drop all this code in the channel. It should be correct. This is your queue, your stack, your graph implementation, the breadth first traversal, and the depth first traversal. And remember, the only difference is whether we're using a queue versus a stack. And if that's not clear why, hopefully that becomes clear and we can talk more about this tomorrow. Only other thing we were supposed to talk about today was we were going to talk about a breadth. Remember, this is a traversal. This will traverse every node in the graph. It's checking to see if it's visited. If it's not been visited, it adds it to the queue. And then when it's been added to the queue, it adds the next neighbors. And for each node, it performs this action. That's how it's not. Remember, I said it may have to check, is it already there, but it does not have to go through and do any of these other actions once it's already, that relationship has been examined. And we were going to talk about with a search. Remember, a search generally is going to traverse either on the breadth first or the depth first, depending on how you want to do it. The implementation will depend on exactly the situation and what you're looking for. But with a breadth first search that returns the shortest path to the searched node, a breadth first search that returns the shortest path to the searched node. Remember, if you're going to return the shortest path, what do we have to do that's different than in just traversing? This traversal, all we're doing with this code is simply going over each node. We're doing nothing else to it besides traversing each node. But if we're doing a search, what do we need to be able to do? If we're doing a search, what do we need to be able to do other than identify if that item, that's simply a one-liner, if this item is equal to the item that we're searching for. And I'll drop the pseudocode for that in the channel if anyone wants to take a look at it, but that may help you out today. And that actually gets us to the end of the material that we were going to be covered. Well, searching, you're going to have to, what I was looking for, but yes, it involves the path, is you're going to have to save that path, remember, because once we find it, if we were just doing a traversal, we have no idea how we got there. We just got there, but you're going to have to save those paths in case you find it, to be able to, as you're going over these paths, finding the path to that. So let me drop that. Let me find out where I've got. Yeah, I had frozen it for just a second while I was going to look for something. So this is sort of the pseudocode right here that we didn't get to cover for a breadth first search. And I'll just talk through it real quick. You're going to make an empty queue. Remember, you're doing breadth first, and on queue a path to the starting vertex ID. Create a set to store the visited vertices while the queue is not empty. Dequeue the first path. Grab the last vertex from the path. If that vertex has not been visited, check if it's the target. If so, return the path, mark it as visited, then add a path to its neighbors to the back of the queue, copy the path, append the neighbor to the back. So this time we're dealing with paths and we're having to keep track of the paths. I'm not going to cover any more of this right now. We can talk about it more tomorrow. We'll actually go through the code solution of that tomorrow. It may be helpful for you today to have this pseudocode. And know that if you do not execute it generally the way that I've got it written out here with the paths, that you can run into a lot of problems. So just kind of keep this general structure in mind while you're looking at what we were talking about earlier when we're talking about your projects for the day. You'll be doing the traversal with the stack, depth first traversal using recursion. Remember, we talked about recursion a lot in previous weeks. And then you'll be implementing the breadth first search and a depth first search. Remember that the depth first, the big difference is that you're simply using a stack and not a queue. But we've covered this today, the graph class. We've talked about a traversal and a depth first traversal with a stack, worked it out. So you've got this code. You're going to implement it with recursion. Then this breadth first search, you've got the pseudocode for, and then the depth first search, you're totally on your own. Any questions, you can speak up in the channel, post it. Thanks for all that have stayed around. I know this ran over. Was trying to do the best I could with the week that we've got with the assembly to get everybody to be able to review the base material that we normally have time to review the pre-class material and go through as much as we could here. So if you have any questions, post them in the channel or ask, or I'm going to go ahead and end this. And I will get this video processed and get the video posted. So remember, jump on your repo, follow the workflow, add your PM as a collaborator. If I'm your PM, you can bet I'm going to be bugging you if I don't see an email that you added me as a collab here after lunch. Get going on the independent project. I've gone over, you've got the link to it. If you didn't have it, I've gone over what you're supposed to be working on today. If you finish today, keep on moving along. If you have any questions, get to the 20-minute rule, get to the help channel, get with your PMs, get with your small group, message me. Thank you, everybody. I will go ahead and end this, and have a good afternoon. We'll see you in a while.